it will be okay. So,
Okay, I hope so. Sorry for the technical trouble.
so can we start?
Yeah, when you want.
Still a few people are joining, but I think that will be, so we can start. So, hello everyone in the seminar. Today's speaker is Frédéric Vincent from the Observatory de Paris. He will be speaking about images and photon ring signatures of thick disks surrounding black holes. So please start. Yeah, just recording.
Okay.
Thank
you. Thank you. Thank you very much, Deborah. And I'm sorry for the technical troubles and the fact that you will not be able to see me. And so yes, I will try to present some recent work on images of thick disks around black holes that were mainly motivated by the Event Horizon Telescope context that I will remind in. And the work I'm going to present is a collaborative work which was done in collaboration with Alejandro Cardenas Avendaño, Sam Gralla, Alex Lutserska, Adrien Pogna, and Maciek Wielgus. I'm known to quite a lot. So let me start with first reminding a little bit of the astrophysics context that probably most of you already know. So I just want to start with this kind of two sides of electromagnetic probing of black holes, at least in my own view. I think that you can see electromagnetic probing of black hole surroundings as divided into two big families. The first one, which is on the left side here on my slide, is when you consider a test particle, so typically a star, orbiting in the potential of the compact object, and you want to follow the geodesics, the typically time-like geodesic of this test particle, and you want to compare it to the prediction of typically GR. This is the first family, and the second family is when you are interested in the innermost matter very close to the black hole, which is typically in an accretion ejection flow. So an accretion disk or a jet very close to the black hole. And these two families have their pros and their cons, of course, as always. So in the on the stellar side, test particle side, the good thing is that the test particle is something that is astrophysically reasonably understood. So a star is something that you reasonably master in terms of modeling. So your probe is well known, and this is of course fundamental when you want to use this object to test the underlying geometry of your spacetime. But the drawback is that typically the star is rather far from the black hole, typically thousands of gravitational radii, so it's not probing the very innermost region of your spacetime. On the other side, the accretion flow, it's exactly the opposite. So the good thing is that you are probing the very, very inner part of your space-time, so typically very close to the event horizon. But the drawback is that there are a lot of things that you don't understand in terms of the astrophysics of the emitting material. So the probe that you are using is very complex as compared to a star. So there are good things and bad things on both sides, and I think it's very, very interesting and very important actually to consider both kind of probes. And you certainly know that there are two very important instruments that are actually trying to use these two kind of probes. Gravity at the Very Large Telescope is trying to follow the motion of the S2 star. So I will not speak of this today, but this is a very, very promising arena for constraining the properties of Sagittarius A star, the supermassive black hole in our Milky Way. And on the right side, the Event Horizon Telescope is what has very recently published the Sagittarius A star image and has published 3 years ago the M87, Messier 87 supermassive compact. So what is interesting actually is when you want to put numbers, when you want to observe this for real, when you want to probe this for real, and you put numbers to check what is the technical requirement to observe these effects, you end up with more or less the same numbers. If you are on the accretion flow side, and you are interested in the two biggest black hole on sky, which are Sagittarius A star, the supermassive black hole in our Milky Way, and Messier 87 star at the center of the galaxy Messier 7. The typical size of the accretion flow, that is sometimes called the size of the shadow, but I will comment on that later, is typically of 50 microarcseconds. So 50 microarcseconds is something extremely tiny. It's the size of a pineapple on the moon. So resolving these scales is a tremendous difficulty, and it's very impressive that the VHT managed to reach these kind of scales. And actually, if you want to do the same thing for the stellar kind of probing, so you are typically interested in this case in stellar motion in our galaxy, because you cannot see individual stars in other galaxies. So if you follow the motion of the S2 star, the closest star to the supermassive black hole at the center of the Milky Way, and you are interested in the lowest order, that I've tried to show on this image with the gradual shift of the orbit with time due to this session. If you make the computation for S2, given the geometry projected on sky, you end up with the same number of 50 microarcseconds approximately per orbit on sky. So whatever probe you are interested in, be it the inner accretion flow or the stellar motion around your compact object, you have to reach these tens of microarcsecond scale to be able to really probe the underlying space-time. And this is what gravity and the Event Horizon Telescope managed to do. So again, gravity, I will not speak at all about this today, but I will rather focus on the EHT, because it's this instrument that is really giving the background to the that I will present. So just to remind, if you don't know this, so the Event Horizon Telescope is a network of sub-millimeter antennas located all around the planet. This picture is showing the 2018 array of the EHT. And of course, you are certainly all aware of this very nice polarized image that was released. So the unpolarized image in 2019 and the polarized image in 2021 of the supermassive black hole at the center of Messier 87, the first target of the DHT. And what is very clear is that with this kind of measurement, you have a fantastic probe to constrain the astrophysics close to the black hole, so to constrain the properties of the accretion ejection flows. So typically, what is the geometry of the accretion flow? Is there a jet? How powerful is this jet? What is the temperature of the electrons? What's the typical magnetic field? Is the jet fed by the energy of the jet fed by the rotation of the black hole? All these kind of very fundamental and profoundly interesting and important questions are directly at hand when you have this kind of images. So for this, it's obvious that EHT images are extremely important for relativistic astrophysics. But what it's not really the aim of the goal of my talk to discuss about this. My point today will be rather to try to discuss, can we say something, and if yes, what kind of things can we say about constraints not on the astrophysics of the flow, but on strong field gravity itself, meaning the nature of the compact object, it is a black hole that we are seeing, and maybe in the future the theory of gravity itself. So before presenting the results that we have obtained with our small group on these kind of questions, I wanted to make kind of hopefully pedagogical introduction on notions that will be important for me in what will follow. The notion of shadows and of photon rings. So these notions are very, very used in the literature, but I have the feeling that there is quite often some kind of the statements that are made on this notion are not always completely precise, in the sense that people use the same word for discussing different things. So I will try to make clear what are my definitions of this notion and why are they or why are they not interesting when probing strong field gravity is at stake. So let's start with this pedagogical section. So I will start with the simplest framework that you can discuss. I'm considering a non-rotating black hole depicted by this black disk here. And you probably know that non-rotating, so Schwarzschild black hole, has a very particular orbit around it, so-called photon orbit, which is a spherical or sphere in Boyle-Lindquist coordinates, where photons can orbit, so they can orbit along this sphere at constant Boyle-Lindquist radius and varying in theta and phi, due to the extreme curvature imposed by the compact object. And this photon orbit will be absolutely crucial in my. So I'm considering an observer. The blue point here is supposed to be a far away observer. And I will consider the typical ray tracing problem, which is that from my observer, I will shoot photons backwards towards the black hole. And I will try to discuss the properties of this photon. Null geodesics that these photons are. So if I shoot a photon that stays rather far from the black hole, it will follow this kind of red geodesic here, so it will just go straight because it's always far enough from the black hole that it essentially doesn't feel the curvature of space-time. So not very interesting photon, this one. More interesting, if you exactly, very precisely aim your photon, it will end up exactly orbiting on this photon orbit around, very close around the event horizon of the black hole. And so if you do this for different angle, different azimuthal angles phi, you end up defining on your sky a particular curve that I will call the critical curve, which is the set of directions such that if I shoot a photon along this direction, they will end up exactly orbiting around the photon orbit of the Schwarzschild spacetime. So this critical curve that I now introduce is a purely mathematical notion. It's definitely not observable. I'm not an astrophysicist now, I'm a relativist. So it's a purely mathematical notion. A notion that is rather linked, or in some way, it's a natural consequence of introducing this critical curve, is a notion of lensing bands. So I will try to make it clear what I call a lensing band, because this notion is probably not so much used in the literature, and I think it's interesting. So let me come back to my previous experiment. So I'm shooting my call it my critical photon, the green one that is exactly aimed very precisely to reach the photon orbit and infinitely swirl around the black hole along the photon. If I shoot a photon that is just a little bit off from the photon orbit, this magenta geodesic, for instance, it will come very close to the photon orbit, but it will not reach it. So at some point, it will leave the surroundings of the black hole and escape to infinity, because the photon orbit is actually an unstable orbit of the Schwarzschild spacetime. So the photon will typically, after a few circling around the black hole, it will escape to infinity. So this magenta geodesics that I have depicted here, it's making exactly 2 half turns, so 1 full turn, around the black hole before escaping to infinity. So as such, I will call it an n equal 2 geodesic. N equal 2 because it's doing 2 half turns around the black hole before escaping to infinity. And I will call on the sky of the observer, I will call the set of directions on sky such that if you shoot a photon in this direction, it exactly completes 2 half turns around the black hole before escaping to infinity. This I will call the n equal 2 lensing band, with magenta in my. So the green curve is the critical curve presented before in the slide before, and the magenta band is what I call the n equal 2 lensing band. So photons that make 2 half turns, 1 complete turn around the black hole before escaping to infinity. And of course, if you shoot a photon a little bit more off from the critical curve, like the blue one here, it will not make two half-turns, it will make just one half-turn before escaping to infinity, and this will create an n equal 1 lensing band. Of course, you understand that you can do that for any number n, so you would have an n equal 1, n equal 2, n equal 3, blah, 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 to infinity. And the n equal infinity lensing band is nothing but the critical curve that I have introduced in this slide. So you have a nested set, if you want, of bands on your sky corresponding to directions of photons that make more and more turns around the black hole before escaping to infinity. So again, here I am introducing purely mathematical notions. I'm just speaking of geometry. I'm not speaking at all about any astrophysics, any emission, of any sort. So these are not observable quantities, these lensing bands. But these are very interesting mathematical loci on sky, and we will see why in. If you imagine now that you have a more interesting sky than only emptiness, each of your lensing bands will actually contain a full copy, a copy of the full sky, which is more and more lensed toward the narrower and narrower region as your number n is increasing. Okay, so for the time being, I have only introduced mathematical notions. So I think it's time to go to astrophysics now. So I will add in my space-time, before I had just a black hole and an observer, which is rather boring. So now I will put an emitting blob of matter, which is this red stuff here. This is like a blob of plasma located around the black hole, close to the black hole. And I will consider different photons emitted by this structure and aimed at my observer far away here. So the first obvious and boring photon that you can think of is a photon that goes straight from the emitter to the observer. This is what I will call an n equals 0 geodesic. So it's doing 0 half-turn around the black hole. It's just going straight from the emitter to the observer. Not very interesting. More interesting, the blue geodesic here, this blue geodesic, this photon emitted by this blob of plasma, is doing 1 half-turn around my black hole before reaching the observer far. This I will call an n equal 1 geodesic, and if you remember the notion that I have introduced just before, this n equal 1 geodesic must be part of the n equal 1 lensing band. And if I now consider even more interesting geodesic, this 1 full turn, so 2 half-turns about the black hole before reaching the observer, this I will call an n equal 2 geodesic, and this geodesic is part of the n equal 2 lensing band. And this is observable. This is where astrophysics really comes into the play. So if I try to summarize a little bit in one slide what I've introduced now, you have the sky plane containing only non-observable quantity, the critical curve, so the set of directions such that if you shoot a photon along this direction, your photon will exactly reach the photon orbit and orbit forever on this photon orbit, and the lensing band. Inside the lensing band, so it's inside the n equal 1 lensing band, you will have an observable feature that I will name n equal 1 photon ring, which is due to photons emitted by the matter located around it, and following n equal 1 geodesic, like this. So doing 1 half-turn around the black hole before reaching the observer. And similarly, you will observe on your sky an n equal 2 photon ring, which is due to geodesics like the magenta one here. 2 half-turns, 1 full turn around the black hole before reaching the observer. And this is the important notion for the relativistic astronomer, because photon rings are observable. Critical curves and lensing bands are pure mathematical notions. They are not observable, but photons are observable. And as such, of course, it's trivial what I will say, but as any observable quantity, that depends on the emitter, of course. If you consider that here you have a blob of plasma located here or located here or there, or that you have a disk or a jet or whatever, you will have different kinds of photon rings still located inside your lensing band. So the n equal 1 photon ring will always be inside the n equal 1 lensing band, and so on and so on for the n equal 2. But they will be different. So this photon ring here is the particular photon ring corresponding to this particular emitter located close to your black hole. So this is something very important to keep in mind, that photon rings, the observable quantity, is something that is not pure gravity. It's, of course, very much influenced by gravity because this geodesic is very strongly curved. So it feels the strong potential of the compact object, but it's definitely not a pure gravity notion. It's linked to the astrophysics. It depends on the particular kind of emitter that you consider close to your black hole. Okay, so this is just like a reminder of the notion that I've introduced so far, and I think that I've already said most of that. So just to say it once more, critical curve and lensing bands, these are pure gravity notions. They don't depend at all on any kind of astrophysics notion. They don't care about the emitter or about absorption or radiative transfer or anything you like. It's a pure gravity mathematical notion, but they are not observable. So as such, for the relative astronomers, they are not interesting. On the other hand, photon rings, these are gravity plus astrophysics quantities. They are not pure gravity. They are influenced by gravity, but they are also very much influenced by astrophysics. And what I consider as very promising observables as far as probing strong field gravity is concerned are these n equal 1 and n equal 2 photon rings that I have introduced. I think these quantities are very promising, and I will try to convince you why I think that in the next section when we finish this pedagogical section. Okay, so much about photon rings. So I hope that the notion of photon rings is now clear. At least you know what I have in mind when I am speaking of it. And now I will try to discuss the notion of black hole shadow, which is also very much used in the and I will try to convince you that according to me, these are not very promising observables, much less than photon rings. Let's try to see why. So to understand this point, I will try to review a little bit some. This slide is certainly well known to most of you. This is the textbook shadow, what I would call the textbook shadow. So what is this about? You consider that you have your black hole, you have an observer far away, and you have a very big sphere, and let's consider an infinite sphere, infinitely far away, that is emitting radiation isotropically. So any point of this sphere is emitting isotropically some constant radiation. I'm asking myself the question, if I'm taking a photograph from this point, what am I seeing? So this is a very standard question. So you can answer this question very easily. If you consider geodesics that is rather far from the black hole, it will go more or less straight from the observer to the emitter here at infinity. And so this direction will transport radiation on sky. And if you consider what I've called before the critical geodesics, the geodesic that is exactly reaching the photon orbit, this thick red geodesic here, this one will never encounter any emitter, right? Because it's orbiting forever around the black hole, so it's never reaching the emitting sphere. And if you consider all directions on sky which are inside this critical geodesic, they will also never encounter any emitter because geodesic that is inside the critical geodesic will simply asymptotically approach the event horizon of the black hole when ray traced backwards in time. So what you will get on sky, this is the image on sky, is an homogeneous field of radiation outside your critical curve, and inside your critical curve, black, it's dark. This is what is typically called the black hole shadow, the textbook black hole shadow. Okay, so this is nice and certainly rather well known to most of you, but it is of course of no astrophysical interest because unfortunately or fortunately, and as you like, there is nowhere in our universe such a uniform infinite sphere of radiation. So the emitter in a realistic context has definitely nothing to do with this textbook case. So what happens is to this shadow if you consider a more realistic setup. So let's consider a setup that is actually reasonably realistic, both for M87 star and for Sagittarius A star. We will imagine that the radiation is mostly emitted in the equatorial plane of the black hole, and it's localized at any radius above the event horizon. So from the event horizon to infinity or to whatever, I don't care. I don't care about the large distance. So. But what is important is that I consider that the emitting matter goes down to the event horizon. So what happens in this case? So we can do the exact same thought experiment. So the boring geodesic is still the same. It's still transporting radiation because it intercepts the equatorial plane, so it transports radiation to the observer. Nothing particular here. If I now consider my critical geodesic here, the one that is reaching the photon orbit and infinitely orbiting around the black hole at the orbit, this one also transports radiation because you see that it's cutting the equatorial plane actually an infinite number of times, so there will be a divergence actually of the intensity on sky. But on an infinitely thin region, so the flux is zero because the width of the critical curve is zero. And more importantly, if you consider now geodesics that are inside this critical geodesic, you see that they too are transporting radiation. This geodesic B here is transporting radiation, so you have radiation inside your critical curve. And actually you have radiation transported by all geodesic inside the critical geodesic down to this geodesic that I have called C, which connects the observer to the inner edge of the accretion flow. If you consider a geodesic that is inside, it will end up at the event horizon, and it will never cross the equatorial plane, so it will transport zero radiation. That's why you still have a shadow, but as you see from my plot, the shadow is much smaller than the textbook shadow because you have a lot of radiation here that is transported by this kind of very strongly bent geodesic that are inside the critical curve. So it's something that is generally, I think, too quickly said in the literature that the black hole shadow is the interior of the critical curve for. This is wrong, I think, because it's only true in this very idealized setup, actually not only in this setup, but it depends on the setup. In this idealized setup, it is true, but in this very realistic actually setup, it is wrong. So the exact shape of the shadow does depend a lot, and when I say a lot, it's really a lot, because my drawing here is not exaggerated. You can have a factor of 2 between the size of this kind of shadow and this kind of shadow. Really extremely different, and it really depends a lot on the geometry of the emitter. Maybe I have spent enough time on the, yes, I think I have spent enough time on the pedagogical introduction. So if you are interested, I can come back on this scenario. This is another reasonably realistic scenario, spherically symmetric distribution of matter around the black hole, radially falling onto the black hole. You can show that in this case, you also end up with a shadow that exactly coincides with the interior of the critical curve, not only the textbook shadow that is like that. Okay, what about black hole shadow? To try to recap what we have seen before, I think the important point that I tried to make in 2 cases that we have seen in some detail. the textbook shadow and the equatorial disk shadow, you see that this is extremely extremely astrophysically dependent. So the notion of black hole shadow is far from being a pure GR notion. And actually, this I should have discussed in this slide that I didn't want to discuss to save time. But you can also show that the very notion of black hole shadow is actually very much linked to special relativistic effect. It's of course very much linked to GR, but it's very far from being purely GR for two reasons: because it's very astrophysically dependent, and because special relativistic effects that are of course nothing to do with GR are extremely important in some cases. So the conclusion from, at least from my point of view, is that if you want to probe strong field gravity, the notion of photon rings is much more promising than the notion of shadows. So I will not discuss much more shadows in the remaining of my talk. I just want to show this image just to tell you, because I have tried to make a point with only pedagogical figures. So you can say, oh, but probably your pedagogical figures are so simplified that it's not like that in the real world. It is like that in the real world, actually, because this plot is showing you an intensity cut along, for instance, an intensity cut along the horizontal direction on the sky of the observer for different models of the accretion flow surrounding a black hole, M87 in this. The purple curve is showing you the intensity cut when you consider a perfectly symmetric distribution of matter radially falling onto the black hole, and you see that indeed you have a very clear shadow that exactly coincides with the size of the critical curve for the particular black hole that we have considered. But if you consider equatorial dominated, so disk dominated accretion flows around the black holes, completely different from the you have something very different. You have here two models, an analytic model, the kind of analytic model that I will discuss in the following, in the black line here, and a GRMHD model in green. By the way, you see that the two are very reasonably similar. And you see that the size of the shadow is very different. It's much smaller than the size of the critical curve, so it's exactly the effect that I have mentioned here as compared to the equatorial shadow is much smaller than the textbook shadow. Okay, so much for the pedagogical introduction. So now that hopefully we share the same definition of the basic quantity, I will try to discuss why photon rings are so promising, in my view, for probing strong field gravity. So let me first discuss this slide, which contains quite a lot of important notion. Actually, all the notion that is in this slide is very much due to this pioneering paper of Michael Johnson and collaborator. It's a great paper, so if you are interested in what I said today, you should have a look, because there are a lot of things in this paper. So we will consider that we are able to image an accretion flow surrounding a black hole. So this is a typical black hole image. So it's the kind of thing that the EHT is imaging for M87 and Sagittarius. And you see that this image of the accretion flow is made essentially of two rather clearly different features. There is a primary radiation, or the n=0 radiation, this radiation that is essentially going straight from the emitter to the observer. So it's kind of Gaussian-like distributed. And on top of that, you have a much thinner ring. So it appears as just one ring, and it's generally called the photon ring. But now you know that it's not just one ring, but it's an infinite sequence of rings, n=1, n=2, n=3, etc., photon rings, the details of which depend not only on gravity, but also on the particular accretion model that you consider. what is very interesting, and what was the key, I think, the key idea of the Judson et al. Paper, is that, well, it's interesting to see these photon rings, but can you image this? Is it within reach of observation? Because the typical size, the typical width of this ring is of the order of 1 microarcsecond. So it can sound like science fiction to imagine being able to detect this. But by the magic of interferometry, you actually can detect this extremely tiny ring. Why is that? Because if you remember the basic property of Fourier transform, essentially the Fourier transform of a Gaussian is a Gaussian. So if you have something that is very broadly distributed, like the primary radiation on this plot here, the Fourier transform, so the interferometric observable, maybe I should have reminded this, but the observable of an interferometer is nothing but the Fourier transform of the image plane. It's simple. So if you compute the Fourier transform of your image here, the Fourier transform of the primary radiation, which is Gaussian-like, let's say quickly, will be a Gaussian, so it will die very quickly with Fourier frequency. On the contrary, if you compute the Fourier transform of the very thin ring, the Fourier transform of the thin ring in 1 digit, the Fourier transform of the Dirac, and you probably know that the Fourier transform of the Dirac is a constant. So it's the exact opposite. It's not dying at all. So here, of course, it's not an exact Dirac. It has some non-zero widths, so it will die with some particular profile, but it will die much less quickly than the primary radiation. And this is what is depicted on this panel here. So the left panel is showing an intensity cut along the horizontal direction of my here. So you see the photon ring, the primary radiation peak on the left, then the shadow, and then the same thing on the right. If you compute the Fourier transform of this, you find that the primary radiation is indeed dying very quickly, but then the n=1 photon ring starts to dominate, and after some starting at some particular baseline, when the baseline is big enough, the n=2 very extremely thin ring starts to dominate. So thanks to the magic of Fourier transform property, you can access your various photon rings. Actually, you can even access to each of them independently if you are able to select your baseline according to what you need to see either the n=1 ring, so here around 100 gigalambda, or the n=2 ring here around 300 or 400 gigalambda. You can select the ring that you are interested in. And if you zoom on the Fourier transform, you see that you have a nice sinusoid signal, and the period of this signal is directly linked to the size of your n=2 ring. So if you are able to do that, you are able to measure the size of your photon ring, which is, of course, something extremely interesting. So there is still one important question, of course, that is remaining when you want to do that. First, is it doable, technically doable, technologically doable? This point of the question I will not consider, but just to tell you, if you want to reach a few hundred gigalambda baseline, you definitely need to use the very long baseline interferometry. So the EHT antennas that are located on Earth are not sufficient. You should have a satellite to give you big enough baseline to be able to access this region. So it's of course an extremely important requirement. You need space VLBI to do that. This is the first point. And I will not go into more detail regarding the question of if it's technologically feasible, can you reach this kind of very small level of flux? Of course, we are at the level of 10 to - 5 Jansky. It's extremely low. But this is not the point of my talk. The question that I want to address now is it interesting to be able to measure this? Because just before, in the pedagogical section, we saw that even the n=2 photon ring is not pure gravity. The size here, what I've called the n=2, the diameter of the n=2 photon ring, depends on the astrophysics. If you have this or that particular flavor of accretion flow, you will have a slightly different value of your diameter. So can you constrain anything regarding gravity? This is, of course, the first question to ask. And this question was actually answered, or at least partly answered, by this very nice paper of by Sangrala, Alex Luxaska, and Sam Maroney 2 years ago. So Sam and Alex are collaborators in the work that I'm presenting now. And these three guys came up with a very interesting idea, which is that, of course, they know that the n=2 photon ring depends on the astrophysics, but what they advocate in this paper is that the shape of the evolution of the diameter of this photon ring with azimuthal angle, so with the angle phi here, so the size d phi of this photon ring depending on the angle phi, because it's not a pure circle. It is a pure circle in Schwarzschild when the black hole is non-rotating, but it gets distorted when the black hole is rotating. So the size is varying with angle. And what they show in this paper is that the mathematical curve that is joining all your points here, the function d phi of phi, this is a pure gravity prediction. It can vary, so it can go up and down depending on astrophysics, but the shape of this curve here will remain and does not depend on astrophysics. It's a very crucial point of the. I wanted here to advocate a paper that I'm not going to discuss today by Adrien Pognat, who was 1 year ago a brilliant master intern with me in Meudon, and in collaboration with Alex Luxaska and Maciek Wielgus, we are very close to finishing. Hopefully, it should be submitted within 1 or 2 weeks. A paper that is trying to go one step further in the analysis of this proposal by. So now comes at least the time of results, because for the time being, I'm just speaking of a pedagogical notion and reviewing the literature. So what did we do? What news am I bringing today? So the research that I'm going to briefly present the results of now is really in the direct sequence of what Sam and Alex have been doing in this paper. So what we have tried to address is the following question. In this paper, the authors are considering extremely simplified scenarios, so purely equatorial plane accretion models, and not taking into account any kind of astrophysics, in the sense that there is not any kind of radiative transfer taken care of in the simulations that they performed. Of course, it's a natural first step, but the important question that we ask ourselves is this n=2 signature, so this kind of curve here, is the detection, or rather is the detectability of the n=2 signal, like in this plot here, is it a very robust feature of black hole space-time, or can it be killed by nasty astrophysics effects? So to try to attack this question, we first developed a simple analytic model of a thick disk surrounding a black hole. So there were already some difficulty in this process, because we wanted our accretion flow to be exactly to be continuous and differentiable everywhere outside the event horizon. This is extremely important, because when you are computing high resolution FFT like we are doing here, any kind of non-smoothness in your model is immediately completely breaks down your FFT. So the proper definition of the analytical model was the first step of our analysis. And then we consider that this disk, that you see that it can be made thicker or thinner depending on simple geometrical parameters that we are using. We are simply assuming that we put electrons in this thick disk. We are prescribing describing their temperature, magnetic field, and density by simple power laws that are parameters of our model. And we compute the thermal synchrotron emission at 230 gigahertz, which is the frequency, the observing frequency of the EHT. And we want to determine whether we see any kind of n equal to photon ring signal depending on the characteristic of the flow. If we for instance, consider a highly spinning black hole, if we consider this or that particular dynamics of the flow, are the electrons, is the fluid orbiting around the black hole, or is it radially falling onto the black hole, this kind of question. So this is illustrated by these figures. This is the results of our study. These are images, so it's typical black hole image of an accretion flow around MH7 here. And in all these panels, we consider a non-spinning black hole, so it's a Schwarzschild black hole. And everything is the same for this picture and for that picture, except one thing. Here, the emitting fluid is orbiting circularly around the black hole. And here, the matter is radially falling onto the black hole. The first thing that you see is that the image is different. So definitely, the details of the accretion flow are important for the details of the image. And what is even more interesting is when you separate your image. So we developed the machinery to be able to cut this image in the purely n equal 1 contribution. So geodesics that make 1 half turn around the black hole, and n equal 2 image. So transported by geodesics make it 2 half turns, so 1 full turn around the black hole before reaching the observer. And so you see that the n equal 1 photon ring is extremely different depending on the model. And so the n equal 2 it's less obvious by eye because it's so thin that it's difficult to see by eye. But if you have a look at the integrated flux on the field of view, 1.6 millijansky here and 0.3 millijansky there. So you have a factor of 5 in the integrated flux, depending on the model. And again, the only thing that is changing between here and there is the kind of motion that the electrons are following. Here they are orbiting, here they are radially falling. So here I think it's a clear demonstration of the fact that astrophysics, so what I call astrophysics, is everything that is not pure gravity. This is definitely not pure gravity. The fact that your electrons are orbiting or are falling, it depends on what kind of source is fueling your accretion flow. It has nothing to do with the particular space-time metric of your compact object. And these astrophysical assumptions have a very strong impact on the n equal 2 observable. But the good point is, I'm not showing the FFT here, but what we obtain is that whatever the kind of motion that we consider for these electrons, we end up with a clear n equal 2 beat. This kind of beating here, this kind of time signal in the FFT, it is definitely detectable. So it goes in the direction of supporting the proposal of Grala-Luxowska-Maroni in the sense that even for a much more astrophysically realistic scenario, you see this n equal 2 signal. So it looks like a robust observable to study the properties of but we were not so optimistic at first when we consider varying the spin. So this panel, the different panels are showing the full image, n equal 1 and n equal 2 image of the exact same setup. So it's a radially falling disk, so a disk of fluid in radial fall onto the black hole. But the thing that is changing between here and there is a spin. Here the spin of the black hole is 0, it's a Schwarzschild black hole. Here it's a very fast rotating black hole with spin 0.94, so you probably know that the highest spin is 1, so it's rather close to a maximal spinning black hole. So the first thing is that, again, you see that n equal 2 photon ring changes a lot. You can see it by comparing the integrated flux. It's a factor of 3 to 4 difference between the two cases in integrated flux just by changing the spin. So it shows again that no, it doesn't show that things depend on the astrophysics. Here it shows that things also depend on gravity. But this example and that example show that both are important. Astrophysics is important. It can change by a factor of 5 your flux. And gravity is important. Changing the spin changes the n equal to ring by a factor of 5 in terms of, by a factor of 3 in terms of observed flux. But what is more important is that if you consider, so this plot is a little bit complicated, I don't want to go into the detail, but these peaks here show the n equal to peak cut along the horizontal or vertical direction along the in the plane of the sky. And the red peaks show the cut in this figure in the horizontal direction. And you see something that is very bad, which is that we definitely see the right part of the n equal to photon ring, but we don't see the left part. It has completely disappeared. Here it is clearly visible on sky, but here it's a log scale plot. So actually the left counterpart of this peak is somewhere, but very, very small, at a very, very small brightness temperature. So this is very bad, because if you have such configuration that you lose one part of your photon ring, you will lose also the sign signal in your FFT. It will not be observable. And why are we losing our n equal to photon ring in this high spin case? Because of very strong absorption along the geodesics that is responsible for the left part of the. So this is really due to astrophysics and to radiative transfer. Here, radiative transfer, self-absorption of thin photon radiation, is killing our n equal to signal in this particular case. Just to show you that it's really bad. This is the FFT that we get for the non-spinning case. So the black is the total FFT, the green is n equal 1 only FFT, and the red is n equal 2 ring FFT. See that clearly n equal 2 is dominating at some point, and you have a very nice beating at 10 to minus 4 density. So it's typically the same as this pedagogical setup that I did first. We definitely see the n equal 2 signal for the non-spinning case, but for the fast spinning case, we lose it. The n equal 2 signal is completely lost because of strong absorption, which is killing our signal. So does it mean that, does it kill the proposal? At first sight, the answer is yes, because you have no idea what is the spin of M87. Well, maybe you can try to have some clear idea on the spin of the black hole with the future flavor of the EHT, with the next generation EHT. But we cannot exclude that it is fast spinning, and if it is fast spinning, our simulations are showing that it is possible that the n equal 2 signal will be lost, which is of course not very good if you want to advocate a space mission. So can we save the proposal? And fortunately, the answer is yes, we can. And it's actually rather obvious how to do it. Here, we are killed by self-absorption, so we have to try to reduce this self-absorption to save our n equal 2 signal. And how to do that? Well, it's rather simple. You simply have to go to higher frequency. If you go to the higher the frequency, the least the smaller the absorption. So this simulation were done at 230 gigahertz. So we decided to check what happened at 345 gigahertz. And 345 gigahertz is not chosen by chance. It's a frequency that will start to be within reach of the next generation of the Event Horizon Telescope. So it's a reasonable value of frequency to consider. And if you go to this higher frequency, if you go to 230 to 345, so if you decrease by by doing that the level of self-absorption, you restore your n equal to signal. And you again end up with a clear n equal to signal dominating your FFT. So I think it's more than time to conclude. And I hope that I have convinced you that photon rings, and particularly I would say the n equal to photon ring, is a very promising probe for trying to constrain strong field property of radiation. We have to keep in mind that they are astrophysics dependent. It's very important to keep this in mind because there are many papers that are discussing, for instance, the critical curve of different kind of space-time, which is extremely important. But you have to keep in mind that the real observable at the end of the day is a photon ring. It's not the critical curve. It's one much more difficult step to do, but I think it's important to do it to really analyze the photon rings and not only the theoretical quantity, which is a critical curve. Yes, I have not given the name of the putative, hopefully to be real someday, experiment, a photon ring telescope, which would be this space VLBI mission with a space millimeter antenna in a satellite to try to perform this imaging of the, not imaging of course, but the detection of the Fourier observable associated to the n equal to ring. And I will, yes, and finally, I think the important result of our own recent work, which will be presented in this paper, hopefully very soon to be submitted, is the fact that this n equal to signal seems indeed robust. So it's not only due to the very simplifying assumption that Sangrala and collaborators have made 2 years ago, that it looks feasible. It also looks feasible when you consider more evolved and more astrophysically realistic scenarios. Okay, I will stop here. Thanks very much for the attention.
Thank you.